second class, and we stumble upon a problem that obviously should have been solved 50 years ago, and it has not. Maybe just no one cared. But they should. It is just the people working on this topic have very different. Yes, exactly. I think that you can do that. Like someone can in this class just like close this question that I will talk about. Because it only requires one to ask the question, and then once you ask the question, you will know how to close it, or someone will figure it out. Yeah, that's why I started to say that many different communities have worked on these type of problems over the years, and CS folks less so. And I think that is what is different here. That we always ask the question about, okay, how long does it take to compute it? I don't know why for the other folks this question never it never occurs to them to actually ask it. I mean, like so you read the literature and it has upper bounds for specific algorithms, but there is no lower bound that says that no algorithm can do better than this and that. It's ridiculous. Anyways, I guess, yeah, it's time. Let's get started. Welcome, everyone. Second lecture. Let's start recording. And let's jump into it. So you can see that this is the contents for today. It's a lot. We'll see whether I can get to the end. Maybe I'm going to do like a two-pass kind of lecturing here, where we first go through what these results are, what they are about, and then we dive into some of the details for some of the results, if time permits it, and as time permits it. But it would be really awesome to get to the end of this and then have some discussion at the end about this open question that I was alluding to. Okay, so I want to start with just a recap of the definitions and actually just reinforcing something that was probably not very clear on the first lecture, which is that if you're dealing with these processes that involve trajectories of infinite lengths, you can't get away without measure theory. Just sorry, you can't. It won't work. So I tried to sweep it under the rug, and I probably gave you the impression that you can. That's wrong. You can't. And today I'm not going to explain this, but I just leave it as a puzzle to you. You have to think about it in a Slack channel. We can discuss what the heck is going on. It's going to be a lot of fun. It could be a separate lecture of what's going on. So with that, let's just jump on this first part of the lecture, which is recapping the definitions. And this is going to be a little bit drier than the last time. So it's just going to be a bunch of definitions. So what is an MDP for us dealing with math? Does anyone want to kind of give me some answer? As a mathematical definition, what would be in an MDP? You can jump on and then just like give me some answer.
Sure. It should consist of a state space, an action space, a transition distribution between states given an action. I think we could include gamma in the definition as well.
Uh-huh.
And I think I'm missing one thing. Let me just
rewards.
Oh yeah,
Rewards,
rewards.
yeah. And
then let's include gamma as well. So just a notation, right? And here S and A, if I'm not saying where they take values in, they take values respectively in the state and action spaces. And you have this gamma. All right, so of course the meaning of this is that you can choose these actions in these states, and then stochastic transition to a next state occurs. And to put this into a rigorous mathematical framework, we were defining, the next thing that we were defining are, so we want to choose the actions in some way, right? Like based on histories. And so the next notion is the notion of a policy. So what is a policy? The way we define it.
It's a mapping between state action pairs to a distribution over states.
Well, the idea of a policy is that it should suggest a distribution over the states. I completely agree with that. The question is, what information can it use?
In full generality, it should have the full history, so the full trajectory of state action pairs that come before a given time.
Yeah, okay, so maybe that was what was meant. Just I wanted to be absolutely clear about this. A policy for us, for a while, if we don't put any qualifiers there, ooh, wow, okay, is this full screen? What is this doing? Is going to be an infinite sequence, because we want to control this process for infinitely many steps, an infinite sequence of maps where each map is going to, each element of this sequence is going to be a map that maps a history to a distribution over reactions. And then here I said a caveat that this is not going to work unless you have discrete state action spaces. So here I'm going to just assume that S and A are discrete. They're at most countable. But let's further simplify, just assume that S and A are finite. All right. So if we put together an MDP and a policy, then the result of that is the interconnection of the MDP and the policy. So there is a policy and there is an MDP, and they're connected in this closed loop. Policy keeps sending these actions and abusing the notation. The action is sampled from this distribution, pi of t, and the history is just going to be S naught, A naught, S1, A1, ST minus 1, AT minus 1, up to ST. This is just a sequence. I don't put in the commas because then it's going to be too messy. This is just a sequence. This goes into the MDP, and the MDP produces an X state. From this distribution that was part of the MDP definition. And so this interconnection gives rise to a stochastic process of an infinitely long sequence of states and actions. Okay? So there is this claim or proposition, like let's call it a proposition, It says that there exists a probability space. Because you know about the prerequisites, you know that like what probability spaces are, and these random elements on this probability space. Oops, sorry. Which is this infinite sequence of random elements. All right, so here I should have said that we should fix a policy, an MDP, and also an initial state distribution. And no matter how you fix these things, there exists a probability space and this infinite sequence in such a way that a bunch of conditions hold. What are these conditions? So first of all, the first condition is that while the initial state is following the initial state distribution. The second condition says that the probability under this probability measure P of seeing an action A selected at time t, given the full history of the process, is just given by pi. So here ht is defined up here. Okay, so that's the definition that's been used. And the third property is that, so far I used mu, I used pi, and of course this holds for every action and every time step. And also for every time step, it holds that the probability of seeing a next state given a history and this action that was chosen is given by these probability transition functions that are defined inside the MDP. So this is equal to PAT and ST, which is part of HT, and S. And this was for every T and for every S. Right? So this allows us to talk about this stochastic process that results from connecting the policy with the MDP, and which is this infinitely lengthy sequence. And what I was alluding to at the beginning is that it is non-trivial whether this thing exists or not. Like, how do you define this? So this is something that you need to show. And for this, you can look up the last chapter in the Bandit algorithms book. It gives you a hint of how you do that. Basically, you have to use the Ionescu Tuccia theorem. And then if you want to know why that theorem holds, then you have to read up on that. Okay? That's how far we are going to venture into measure theory land for now. It's fun. Okay. So since this probability measure depends on pi, depends on mu, depends on the MDP, we could index it with all of these things. The MDP is usually fixed, so we're not going to show it. And but many times it's going to be important, the dependence on the policy and the initial state distribution is going to be important. So in that case, we're gonna denote this dependence is like a lower index and an upper index. So this is the policy, and this is the initial state distribution. And if you have a probability measure, then you have the corresponding expectation operator as well. So we can, using this this stochastic process of state and action sequences, we can create other random quantities. For example, we can create the return. And the return is just going to be defined because we're in this discounted MDP as the sum of total rewards, discounted total rewards along the trajectory. Since ST80 were random, this is also random. We can take its expectation. Oh, and if the initial distribution happens to be the Dirac distribution that concentrates on the state S, then rather than writing this lengthy delta S pi notation, we just use PS to denote the dependence on the initial distribution. That is like, okay, you start at state S intuitively. And similarly for the expectation operator. And this allows us to define the value function of policies. So if you have a policy, then its value when you start a policy at state S is going to be the expected value of the return under the distribution that is generated by the interconnection of the policy and the MDP and the initial state distribution, which is concentrated on S. Okay, so to write this, you just have to write that this is ES. Expected value of the return with respect to this distribution. Okay. The objective in MDPs is to maximize the values. So the maximum value that you can get in a given state is just defined as the max over all policies. Sorry, it's like of the values that you can get. Can someone tell me what are the potential problems with defining the values this way?
The space of policies might not be compact, so we might need a supremum instead of a max.
Right. So this set could be something like, you know, the 0-1 interval, which is open on the right, and then how do you take the max? Like the set of possible values could be such that. And then the max doesn't exist, so that doesn't make any sense. So we write sup here. Okay? All right, so this is the definition of the optimal value function. And we aim for a policy. So the goal is somehow to find a policy such that it agrees with the optimal value, its value function agrees with the optimal value function at every state. So from here on, you will see me suppressing dependence on states. So that just means that they agree as functions, which means that they agree at every point, point-wise agree, okay? Similarly, I might write v of pi smaller than equal to v star, by which I mean that point-wise, for every state, the value taken by a policy is smaller than equal to the optimal value function. This is a true statement, right? Because of the definition of v star. So in a way, here the challenge is to somehow find a v pi, a policy pi, such that v pi is also above v star, right? Like, is this possible? Of course, if this happens, then they have to agree, right? Okay. And more specifically, the goal could be to also efficiently compute such a policy. And if you can't really compute such a policy, then the second best thing that you could try to do is to compute a policy such that its value is close to optimum. So it's epsilon close to optimum. So I'm going to write this 1 to mean the function over the state space. It's kind of like hidden in the notation that maps every state to the value of 1. Okay? So that's just the constant 1 function. And this allows me this nice arithmetic between, you know, comparing this or like adding and subtracting like epsilon, subtracting epsilon from every value. So that can be written in this compact manner. Okay? These shortcuts are going to be quite useful because we're going to save a lot on writing. Okay? So a policy that satisfies this is called an epsilon optimal policy. And what you should imagine is that someone hands you the definition of the MDP. So it's finite. So just big tables of the transition probabilities and the rewards. It's like a graph problem, actually. And then you have to come up with a policy, which seems to be a very complex subject. I mean, like, these policies were, you know, dependent on the history. It's an infinite sequence. Like, we will never do that, right? We want to come up with much simpler objects, much simpler policies that have a compact representation that can be compactly written, such that if someone would execute this policy in this MDP, the values that they would get at every single state, would be epsilon close to be optimal. So one class of policies, which is of particular interest because it has a very compact representation, is a class of memoryless policies. I'm going to write a lot of times memoryless, so I'm just going to abbreviate it to ML. Hopefully it's not going to cause much confusion. So what's a memoryless policy? Memoryless policy doesn't quite remember. It sees the last state and reacts to it. It's the absolutely reactive policy. It can still use the state information, but it can't use the history. It has to forget the history. So as such, a memoryless policy can be identified with just a map that takes a state in and then returns a distribution over the actions. Okay? So that's the definition of a memoryless policy. Now you might be wondering, but okay, like, but how do I execute this? Well, as you would think, so if you go back to this diagram here, when you have a memoryless policy, then it doesn't remember. So it's instead of HT, it will only have ST. So it sees the state, the last state, and then it reacts to that. It just like blurbs up some action as a reaction to the state. And the first question to ask, are we going to lose something if we focus on memoryless policies? Maybe the best value that we can ever achieve with memoryless policies is going to be strictly less than the best value that we could have achieved with unrestricted policies that can use arbitrary memory, the full history. Well, the answer to that question, to break the tension, is no. You're not going to lose anything. So that's the, I like to call the fundamental theorem of MDP or dynamic programming. So that's our first theorem. If we take pi to be the greedy policy, oops, and I will explain what a greedy policy is in a moment with respect to V star. So every policy which is greedy with respect to V star, for every such policy, it holds that this policy is optimal. Its value function agrees with the optimal value function every state. So that's the first part of the theorem, and then it has a second part, which is that the optimal value function satisfies this equation, which I'm going to explain in a moment, which is called the Baman optimality equation. All right. So the things which are undefined are greedy and this T. So what's a greedy policy? It's a policy, we say that pi, so this is the definition, pi is greedy, pi, let pi be a memoryless policy. It's greedy with respect to some function that maps states to reals. If the following holds, you do what's called a one-step look ahead. You kind of pretend that V gives values for the future. So you just say that, okay, let's pretend that whatever the future holds is summarized compactly by these values. And then let's test what would happen if I choose an action A. and what would be the total value that I get. And the total value would be, you know, like the immediate reward, because in the return, like we had just this discounted sum of rewards. So you would have the immediate reward plus gamma times all the future rewards. And now the future rewards are under expectation that, like, you're thinking that you are in state S and taking action A. So what's random here is the next state. So you're transitioning to a random next state. So an expectation, the value is kind of going to be like this. If from that point on, V was faithfully representing what values you would get, this would be a prediction of, like, what's the total value that I can get if I try this action A in state S. Okay? This is also called a Baman look ahead. Richard Baman in the 50s somehow figured out that feedback was important, and, like, he came up with MDPs, and a lot of these theories in some way are theoretical results. The very basic foundational theoretical results go back to him. So that we are honoring him by naming a lot of things after him. Anyway, so just the definition so far. And it's too much writing. So I want to introduce this inner product notation. So instead of this sum, I can just write, remember that PAS is a vector of probabilities. I can just take the inner product between this vector of probabilities and V, and then that's the same thing as this sum, right? Just using inner product notation. And then I can write the same thing. And so now I can do two things. If I have a policy, I can follow the policy. Following the policy means that I just take the expected value of these value predictions of imagining that you take this action A in this state S, multiply it with what is the probability that you're taking this action, and then summing it up over the actions. Okay? And the other possibility is that you deviate from this, and you say that, well, I have a better idea. Maybe we should take the action that gives me the highest predicted return. Okay? So then you would just, instead of using the policy, you would say that, let's take the max. All right? So now I'm going to erase this. So to finish the definition, we say that a policy, which is a memoryless policy, is greedy with respect to a function V if the following condition holds. For every state, if you look at the value, total value predicted by using the policy is the same as the total value predicted if we wanted to maximize the predicted values per state. Okay? Again, this is too much writing. We don't try to write this much. So you're going to introduce a bunch of other notation. And you're going to be overflooded with this notation at the beginning, but I hope that, well, eventually you get used to it, if nothing else. So we write a lot this sum over the policy-weighted rewards. So let's just call this R pi of S, okay? So that's just like the mean reward, mean immediate reward in state S if you're following this memoryless policy pi. Okay, that's simple. And I can also move this sum inside this probabilities, right? And then I can get something there. So that will result in this stochastic matrix P of pi that I'm going to define on the next page. I guess I just have to move on to the next page. I don't have enough space here. All right. So bunch of definitions. R pi of S, that's just like the immediate rewards. And I can just write R pi and pretend that this is a vector in RS. I can identify the states with the first few positive integers, and then this is just an element of vector space, and the usual rules of calculating this vector supply. So from now on, you can imagine that this state space is just the first S integers. This is calligraphic S, and this is like Roman S or whatnot. You need to make a distinction between those. Same with the actions. And then the pi, P of pi, I want to define it as what's the probability of seeing the next state S prime under the policy. This is the probability of seeing next state S prime. And I can pretend by moving this S and S prime into the indices that this is a matrix. This is, for S and S prime, S is the row index, S prime is the column index. This is a matrix. This is a stochastic matrix. It's an S by S matrix. And the next notation is going to be this map that maps RS to RS. So T of pi applied to V is going to be just R pi plus gamma times P of pi V. And if we look back, this is what you see here, evaluated at state S. I just wrote it with matrix and vector notation. Okay. Similarly, we want to invent another function that summarizes this max business. So I just write it out here. So there will be another function that maps RS to RS. And this function is, takes a V. And then if you want to know what value it takes at state S, I better write it this way, because otherwise I would have to say that it calculates the maximum over all of this big table with respect to the action, and that's a bit confusing. So here I can just say it takes max of A of RAS plus gamma PAS V in a product. All right. And another convention that you will see a lot is that we don't like to write that many parentheses. So from now on, instead of T pi V, we allow ourselves to write T pi of V, the same with this operator. So what happens then with things like TV and S? Yeah, T has a higher precedence than taking the value of the results. So this parenthesis operator has a lower precedence. So this is defined as first applying T to V and then taking the value at S. Otherwise, it wouldn't be even syntactically correct. Like the other way of interpreting things won't work at all. And sometimes, if we really want to emphasize that these are also vectors, then we can write the S as an index. Okay, all these notations. So with this, what is this notion of being greedy? Well, pi is greedy with respect to V if T of pi V is equal to TV. Okay, much shorter. And we killed two birds with one stone because we also introduced the operator T, which is called a Baman optimality operator. So T is called the Baman. All right, so that's a fancy word, operator. Operators. Are we doctors or something that we're operating on patients now, or what's happening? Well, I think mathematicians got bored of calling everything maps and functions, and so they invented another name. It happened a long time ago. It's called an operator. It's the same thing. I don't know why it exists. So T is called a Baman operator. I guess what happens is that at the beginning you had functions, value functions, and then you have things that take as input, functions and return functions. That's crazy, call those functions. You have functions and functions. Of course you have functions and functions. But okay, why not call them with some fancy name because they're operating on functions? But if you think about it, functions are just vectors. And like since when do we like to call something that operates on vectors to be something really special? Well, okay, forever. Like mathematicians decided early on that this should be called operators. So they're called operators, but they're just functions. And for reasons that will become clear later, T of pi is called the policy evaluation operator of policy pi. All right, we should maybe stop. Do you have any questions?
So one of the major questions is this theorem assuming Markov property, or are we assuming Markov property? When did you say that? And one other was, does V star even exist?
Okay, very good. Why these questions? Markov property. Oh, I should. Struggling with this technology still. Anyway, so Markov property is hidden here. This is called a Markov property. Actually, both of these are the Markov property. Sort of. Right? Well, the first one is arguably not really. So what is the Markov property for those people who don't know what the Markov property is? Markov property says that if you are in this very special stochastic process, distribution over the future condition on the current value of the process at time step t is the same as the distribution of the process for any future event whatsoever conditioned on the full history. So the state summarizes the history. And here, this is it. Here I have the full history, conditioning on the history, and it's gone. On the right-hand side, I just say, well, sorry, it only depends on ST. So you can throw away anything else from the history. The governing distribution of the next state is only dependent on what the current state is. It doesn't depend on what happened before. And the reason this theorem is going to hold is indeed like, yes, like this is the essence of a Markov decision process. You can forget about the history. And then, of course, memoryless policies don't need to remember the history either. It's kind of intuitive. Takes a bit of effort to prove it. So that's part one of the answer. By the way, this is called the weak Markov. Sorry, this is called the strong Markov property, and there is something that's called the weak Markov property. Doesn't really matter for us. The other question was, is the optimal value well defined? Well, if you believe in that supremums are well defined, it should be pretty well defined, right? You might ask, like, okay, does the set of all policies exist? Of course it does, right? Especially in this case. Now we are going back to foundations of mathematics, which sets exist, which set don't exist. Does the supremum always is it always well defined? Well, as long as the constituents are well defined, it's well defined, right? I don't know whether there was something more to that question.
There's one more thing, but does such a pi exist which will achieve this V star?
Oh yeah, that's a miracle. That's what the theorem says. It does. Well, here, hidden assumption is that S and A are finite. And we also assumed all the way, well, if S and A are finite, it's not a big assumption that the rewards are bounded, because then of course they're bounded. But like, if you start to go into the land of infinity, then none of this can be taken for granted, and everything is going to be painful. Because maybe you need to only prove that epsilon optimality exists, blah, blah, blah. So you have to be very careful. Maybe it's going to be a homework to check what survives if we start to lift the condition that everything is finite. But for now, finite is good enough. It's a good question. Yeah.
I was just going to ask about, like, when he wrote this as like the inventory control PDE, and was that finite?
The inventory control PDE. Who wrote that, or
like wasn't like kind of a lot of the original like Baman work done for this inventory control?
Right. No. Yeah, like these theorems shouldn't be attributed to him by any.
Okay.
In any ways. He was actually quite funny because he looked at very many special examples, but he was not on the top of proving, like theorems in this field, which would be any general. No. At least I didn't see that in the books that he has written. It was some other people who were like, oh yeah, like we have these theorems. Nevertheless, I think he had the right ideas about a lot of things. A lot of these things. All right. Are we good?
There's maybe another question. So this theorem is about the probability measure that's constructed using the proposition before, right?
I mean, V star, V pi, everything is defined in terms of those probability measures. So yeah, we can't escape that.
Right. So implicitly, it is using the Markov property, because that stochastic process was constructed.
Absolutely. Yeah. I mean, everything goes through that, right?
Yeah.
It's kind of funny, this. Maybe I shouldn't call this a proposition. It should be a big theorem that these probability measures exist, because it's kind of funny that it's usually swept under the rug, but it creates the foundation for everything. Otherwise, how do you even talk about these things? And control people have always been doing this, and OR people, like, they were well aware. I mean, like, I think the last time I was bragging about that MDPs made an impression on pure mathematics as well through measurability questions, but yeah. And that starts with that. Anyways, so making some progress. So this was the fundamental theorem. And you may wonder about how to prove this. And how do we prove the fundamental theorem proof? There are many proofs. The proof I like today is the one that goes through discounted occupancy measures.
Quick clarification.
Yes.
Fundamental theorem is the theorem stated earlier. Like, will we refer to it as the fundamental theorem?
Yeah.
Okay.
This one.
Okay.
Let's make it clear. This is FT. All right. So the proof would be a few lines if we defined the optimal value function slightly differently. If we define the optimal value function, so let's define this alternative optimal value function as at state S as the supremum over all policies which are memoryless, which forget the memory. Oh, okay. Toffee disagrees. So it's a maximum value that you can get with memoryless policies. And then it's easy to prove that if pi is greedy with respect to this modifiedly defined optimal value function, this restricted optimal value function, then the value function of pi is going to agree with this. And it's also easy to see that this guy satisfies this equation. So if you apply t to this guy, it returns the same thing. This is called a fixed point equation. I said that this is the Baman optimality equation. And all the pain is to show that v tilde of star is equal to v star. Now, of course, we know that it cannot be more. So that's clear. So the question is whether this holds. In other words, the proof can be done in two steps. Like, first you show this, and then you also show that this holds. To show this second thing, that's a fun thing. For this, the shortest proof that I know about uses what's called discounted occupancy measures. Or just occupancy measures. So if you fix an initial state distribution, you fix a policy. Of course, we have this fixed MDP. Then this gives rise to a measure over the set of state action pairs which is defined the following way. This is finite set, this set of state action pairs. We can just define the measure by stating what values it takes on each element of this set, that is on every state action pair. And for a given state action pair, the value assigned to it by this measure is going to be the infinite discounted sum of the control process that is started from initial state mu, and the control follows policy pi, hitting in various time steps this particular state action pair. This is definition. All right. So there is something really nice about this definition. It's very useful to study the values that a policy is going to take, right? Because if I care about what's the value of this policy at state S, I can just write it as the sum over all state action pairs of the weighted sum with respect to this discounted occupancy measure of the immediate rewards in those state action pairs. By the way, another abuse of notation, I'm just going to write this as nu of mu of pi and the inner product between this and R. But here R is viewed as a vector in this SA dimensional space. Okay? Just the definition of the inner product. So why is this true? Well, the value of a policy was defined like this. Right? And then I can just start to condition and then swap sums, pull out the comma. No, not this order. And here I'm going to insert an indicator that filters out everything except when the state hits this particular state S and the action hits this particular action A. So you know this indicator notation. So the indicator of, I don't know, whatever logical expression I write here is equal to 1 when the logical expression is true, and otherwise it equals 0. It basically converts true and false into 0 and 1. It's just a conversion operator. Okay? So of course, this sum could be inside here. And if you sum up all these indicators, we listed all possible state action pairs. So all those indicators sum to 1. It is also called the law of total probability because we like to give everything its own unique name. All right. And then I can move this sum outside of the expectation. And I can move this sum outside of the expectation. And if you want to know why can I move sums inside and outside, well, look up chapter 2 in the Banach books, in the Banach book. Anyways, so once you have this, you can notice that if you have this indicator, then I can just replace this. Here there is this RAT, ST, where AT and ST are random, but I can replace them with just A and S. That doesn't change the expression, right? So in details, RAT, ST, indicator, ST is S and AT is A. That's just the same thing as RAS. The indicator that ST is S and AT is A is left there, okay? Why? Because either the indicator is 1, in which case they are the same, or the indicator is 0, in which case they are the same. So a simple case analysis shows that they are the same. And now, since we have this RAS, so I can just replace this with RAS. That's just the value. That's just, you know, a number. I can pull it out of the expectation, right? And the expected value of an indicator is just its probability. That's the definition. What's the expected value that, you know, you hit this? Well, that's the probability of hitting it. It was the definition of the expected value. So because of that, okay, so continuing this expression, why is it that, like, if you start to derive anything, then it happens in the bottom of the page? I don't know. So there is this sum over states and actions, and then sum over time steps, comma t, and I can pull out RAS, and then the probability that we are hitting this particular state action pair remains. And I can pull this outside of this sum as well because it doesn't depend on t, right? So note that I've separated them. And then what remains here is just the discounted occupancy measure, the value it assigns to this state action pair SA. So this is indeed equal to the inner product of this discounted occupancy measure under mu and pi and the immediate reward. All right? So why do we care? Well, eventually the values are what matter, and this is a very simple expression for the values. In a way, if you care about the value at initial state distribution, it tells you that you should just think about, like, what are these occupancy measures, and then try to choose the policy such that it's most like occupancy measure is mostly aligned with the reward function. You can think about the reward function as, you know, as this vector. This is a reward function, this vector in this RSA space. And then the control, means that you're choosing some occupancy measure and you try to align it with R. If you can do that, the better you can do that, the more value you're going to get. All right, so that's why we care about occupancy measures. So we want to understand hold on to the question. We want to understand the space of occupancy measures. And for this, here is the big revelation. For every pi and for every mu initial state distribution, you can find a pi prime memory rest policy such that it reproduces the occupancy measure of pi. So if you concentrate on just occupancy measures, you realize don't need to worry about policies with histories. They don't add anything. It's kind of understandable. So just a hint for the proof. So somehow we need to construct this pi prime, and we are given an occupancy measure. And of course, if you have a memoryless policy, then that's also going to induce an occupancy measure. And so somehow you want to do it in such a way that like you get a fixed point. And the operation is just like almost like the only thing that could possibly work. This is not foolproof, but the idea is that you try this. You take the policy pi prime that is roughly going to follow, well, it's going to follow the distribution that is given to you as the discounted occupancy measure, but of course this is not really a distribution. You should normalize it. So you're going to normalize it by summing up things. Okay, so let me introduce this notation. So the nu tilde mu of pi of s. So that's just the marginal. If you sum up the occupancy measure over the action components, marginalize that away, then the result is another measure. It's over the states only. And of course, if you if I now divide by this sum, well, assuming that this is non-zero, and otherwise we can take any distribution. Then this is going to be a probability distribution at least. And this is what you can hope is going to work, because if pi was itself memoryless, this is how you would get back pi from the joint state action distribution or occupancy measure. Then this would work. And then, okay, like, will it still work? Well, that's a little calculation, but that's basically algebra. So whenever in a theorem you see an equality, then you can be sure that there's going to be a few algebraic steps. Almost always it's just like just writing something. And here the hint is that you should check how the occupancy measure over the states look like for memoryless policies, and they will satisfy a nice identity, and they're going to be the unique solution to that. And then you just satisfy that this other measure is also satisfying it, and then you're done. All right. So this is the theorem that allows us to focus on just the memoryless policies. Why? This immediately implies that V tilde star is equal to V star, right? How come? So V tilde star of S. Well, okay, let's start with V star of S. So V star of S was the supremum over all policies. Yeah, okay, so let's take a policy pi, arbitrary policy. Maybe it uses memory, maybe it doesn't. And then V pi of S is going to be the inner product of, okay, if I want to write this, with this mu being delta S, then I allow myself to write just mu S pi, okay? So mu S pi and the reward. And so since there exists a memoryless policy that reproduces the occupancy measure underlying pi and S, let's call this memoryless policy just ML pi. So this is equal to the occupancy measure of this memoryless policy. So now take the supremum of both sides. So I get on the left-hand side the optimal value function. And here I'm taking the supreme over all of these guys. Okay, so these guys. So the supreme over all pi mu s ml pi r. But inside, when I take a pi, I switch to just the set of memoryless policies. So I get something bigger if I take all the pi which are memoryless, and I take their underlying occupancy measures and take the supreme over all these inner products, right? I increase the set. So possibly earlier, I only had a subset of these memoryless policies, the ones that were selected by the non-memoryless policies. In reality, they are the same, but we don't care for this proof. So potentially, I enlarge the set, and on the right-hand side here, we have, it's hard to see, we have the supreme over all memoryless policies. So that's just V tilde star S. I'm struggling with this space. So we see that this theorem does imply that V star is less than equal to V tilde star. And of course, we knew that V tilde star was less than equal to V star, so they are equal. and we are done. All right. Next thing. Oh, there were some questions, and I said that. Okay. Oh, the set of memory-less policies is not bigger. So here, I access. Okay, so this accesses potentially a subset of all the memory-less policies. The question was, why is the set of memory-less policies bigger than the set of not memory-less policies? It's not bigger. What I'm talking about is that here I'm accessing potentially a subset of all memory-less policies, right? Because like, who knows? Well, the only thing we know about this, that these are memory-less policies, but are they all? Well, maybe not. Like if I replace this with an arbitrary memory-less policy, this index here, then maybe the supreme is over a bigger set, so maybe I get a bigger value. Of course not, but that's the logic. Okay, there was some other question. Oh, do we have a similar geometric intuition for stochastic rewards? Yeah, that's. So I never addressed the question of stochastic rewards. You can take the stochastic rewards, okay, so there are multiple levels to this. But basically, you can take the expected immediate reward just for states and actions, and everything goes through. So it's like all the rest of the stochasticity of the rewards. If they depend on future far away states, then that's a problem. Then you don't have Markovness. You don't have anything. But standardly, sometimes people assume that the reward depends on the next state, or it has some additional randomness, but it still satisfies similar Markov property. Then, like, you can just take the immediate rewards defined the way I'm defining it here, by just taking expectations. So it reduces this computational theory. Just reduces to this setting. There is no role of what if the rewards depend on the next state. It doesn't matter. You can take expectation over that. I already kind of do it implicitly. All right. So next thing, how do we compute anything? I mean, like, this fundamental theorem is great because it creates the hope that we can find a policy efficiently and effectively if we can identify V star, right? So without this fundamental theorem, how would you find a policy that dominates pointwise the value function of all the other policies? So you can, there is another geometric picture for this value function. So this is value functions there, space. And so here the domination is that if coordinate-wise on every coordinate you're dominating, then you're dominating it. It's like, it's gonna be hard to draw, but like you have this, and then like, okay, which the higher values are bigger, like in all respect, like in all along all axes you have to go further, so you have to choose something here, something there, something there. So if you do that, then this guy is going to dominate. And so, and you are trying to, you have this point cloud of all the value functions for all the policies. And you're trying to identify this single dominating point. Like, it's a miracle that it does exist. Like, this set has a very miraculous structure. In general, it doesn't exist. And then you also try to find the underlying policy that like give rise to that. And how many memory-less policies do we have? Even if we just consider deterministic policy. Oh, by the way, the fundamental theorem also implies that deterministic policy can be optimal. Like you can find an optimal deterministic policy, but interrupting myself. So it's kind of a miracle that this exists. And how many deterministic memoryless policies exist? Well, it's every such policy is a map from states to actions. So this is their number, a to the s. So exponentially many. And if you want to enumerate all of them, and then, like you have exponentially many points here, even if you're just searching the space of memoryless policies, and then find is dominating, it's going to take forever. It is not very hopeful. So now the fundamental theorem says that if you know V star, then you just find a policy, a memoryless policy, that satisfies this. Okay, writing it out, it's basically you have to find an action in every state that maximizes the one-step look-ahead values at those states. And so the computation of an optimal policy, the way it's going to look like, first, compute V star on an approximation of it. Second, find greedy policy with respect to V star. The second step is here. That's a trivial computation, right? So this is going to cost you OS. Here, these argmax cost you OA. Well, these are elementary operations, just adding and multiplying. And you have S states, so this part is going to cost you OS squared A. If by finding a policy we mean that you need to specify what action that policy takes in every state. So just writing it down is going to take S times A numbers or something, units, right? And so what we hope is that we can compute V star efficiently and effectively. And lo and behold, the second part of the fundamental theorem said that TV star is equal to V star. And that, well, it's probably not clear that this makes me hopeful, but if you see something like this is called a fixed point equation, then one of the first ideas that comes to mind is a fixed point iteration, what's called a fixed point iteration. So you start with an arbitrary V0, maybe the all zero function. And then you say that Vk plus 1, let it be T applied to V of k. All right? And under a number of conditions, such fixed point iterations converge. And very often you can even get the rate of convergence. And lo and behold, that's the case here. So you can prove that Vk minus V star is smaller than or equal to gamma to the power of k. Sorry, here I have to use a specific norm. That's the max norm. And the V star, because we initialized it at 0. The reason this holds is because T is a contraction operator. So what that means is that if you take two different vectors, or let's just V things, V and U, and you look at what T does to them, it pulls them closer together. and pulls them closer together by a factor of gamma. Okay, this is called a gamma contraction. And it is Banach's fixed point theorem which says that if you have gamma contraction over an appropriately normed space, so the space should better be nice, but our space is nice, then T is going to have a fixed point. It's going to be unique. And this fixed point iteration is going to satisfy this property. It's going to converge exponentially fast. This is an exponential fast or linear or geometric convergence, depending on which community you belong to, because gamma is smaller than 1, and these values go to 0 really, really fast. So if you want to decrease the distance between Vk and V star below an epsilon, then you have to solve what's the smallest value of k such that this hold. Well, the first thing that's going to be useful is to know that V star cannot be too large. V star is at most 1 over 1 minus gamma, where I'm using the assumption that the rewards are between 0 and 1. If they were in some other interval, it would be the span of the interval that would vary. The weights of the interval. And okay, now we need to solve. If we don't know how big is the max term of V star, then we need to solve for the smallest k, and you can do that, and then you will see that it's like log 1 over epsilon dependence is going to show up. It's log 1 over epsilon. There is some 1 minus gamma in the log as well, divided by 1 minus gamma. That's basically the bound. And then you have to hope that if you're approximately solving this, like you find this Vk, you stop whenever this holds, you gridify, it's still fine. So that remains to be seen for the next lecture. And obviously, I didn't cover as much as I wanted, but it's all fine. Like, we are still on track. But I should stop here. It's too much to cover. So let me just take, if people need to go, then they can go. And if there are some questions that are interesting for everyone, then maybe we're going to post it on Slack. I'm happy to stay a little bit longer.
Sure, but there's a question in chat.
Okay.
And the question is, suppose we have a policy that's greedy with respect to epsilon optimal value function, then is its value function still epsilon optimal?
No, there is an extra 1 over 1 minus gamma inflation. And we're going to cover that. It's 2 over 1 minus gamma inflation, to be precise. And yeah, good thinking. There is an inflation of the error. So this epsilon, if you really wanted to have an epsilon optimal action, you have to prepare and choose an epsilon which is already inflated back, right? Like divided by the inflation factor. So that you have to go a little bit longer. But the good news is that this process is exponentially fast. It's like log 1 over epsilon. That's really awesome. Not too many iterations are needed to get something really good. Yeah. We're going to be precise about this, and the next time I'm going to talk about the computational complexity. Oh, I didn't say, but this process, this iterative process is called value iteration. So maybe I just put this on a slide so that it's obvious. So this is called value iteration. And we're gonna be more precise about what's the computation complexity of value iteration. There will be some other process. It's called policy iteration. And I will show you some bound and computation complexity of policy iteration. And then we will ask the question that should have been asked much earlier of, can you do better than these? Are there any procedures that would be able to do much better than either policy iteration or value iteration? And I will tell you what is known about it, and it will turn out that not much is known. So there is a gap between the lower bounds, the algorithm independent lower bounds, and the upper bounds. It's quite fascinating. And that will end kind of like the very first block where we are just talking about this. Like, how do we even take off from the ground by, like if someone came up with very small MDPs so that these epsilon optimal calculations are feasible. Well, we'll see from the lower bound that the lower bound will at least say that you have to touch every state action pair at least once. So in a large MDP, no algorithm can do better than, like touching every state action pair at least once if you're demanding to return a policy. So that kind of not too hopeful. And then we start to ask better questions about like, okay, if your MDP is large, maybe you shouldn't demand that you compute a policy that figures out what to do in every state. Like, why do you care about states that you're not at? And then we'll see that there are some interesting variations there already. And then a lot more other things are going to come. Okay?
I just had one question. The right-hand side, where you have TV minus T smaller than gamma, like, is that an assumption, or like, why is that true?
No. So this was a this is a proposition or theorem, if you wish. So this is a proposition that this is true, and then we call this function a gamma contraction, or this operator a gamma contraction. So definition of a gamma contraction: T is a gamma contraction in general if for every U and V, the distance between U and TU and TV gets smaller by this multiplicative factor of gamma, which is smaller than 1. Since it's smaller than 1, it's called a contraction. If it was just like some other number, like 2, then it would just be called Lipschitz. If this number happens to be 1, then it's called a non-expansion. There are all these names. Yeah, and then this is a proposition that one needs to show, and it's not hard to show. It's an elementary thing to do.
Chaba, I have a question. So for this theorems, so I was thinking in the case of, I know this is evolving with respect, like the process is evolving with respect to the proposition that you stated earlier. So what happens if you have, like, say, partially observable? This theorem probably would not hold, right? Like if you have function approximation, so you don't have all like fully observable states.
I mean, the theorem does hold, right? Like, what does the theorem say? The theorem is like really precise. It says that if you have an MDP, this happens.
Right.
If you don't have an MDP, it doesn't say anything, of course.
Yeah,
right?
yeah. I guess what I was saying is in the situation, if you have like function approximation, like if you take the full history into account.
So you're talking about, I guess, like, for example, this previous theorem that says that you can reproduce all these data measures.
Yeah.
No, that's not going to be true.
That's not going to be true. So even if you take the full history, this still would not be true.
No, I mean, like, memory-less policies are strictly less powerful if you don't have full observability.
Right. Yes, obviously. Yeah. So then in this case, the theorem cannot hold. I see.
Well, yeah, like none of the things can hold that. Rely on the Markov property, right?
Okay. So okay. So you're saying you can't say anything in that case with respect to
Well, you can say other
theorem
things, but not these things.
Okay.
Yeah.
Yeah. Okay. I got you. Thank you.
So for PlumDPs, of course, there is a reduction to MVPs, which works through the belief states. So in a way, you could argue that the MVP is the basic case, and that you can basically reduce everything to it. But that reduction is useful or not, that's a different question. Tutto quello mi ci Akkor vidd el onnan. All right, I think I should wrap up. The doggies don't agree that we just go on. We can continue in Slack and then next time, all right? Okay, see you guys.
Bye, everyone.
Thank you.